Hello everyone. In today's video, we are going to learn about linear programming in operation research. So let us begin. First of all, we will learn about the definition of linear programming. So it is an optimization technique which is helpful for finding an optimal solution for a problem to maximize the profit and minimize the cost. It has four components. Those are decision variables, objective functions, constraints, and non-negativity. These four components create the formulation of linear programming. Now let us know what is a decision variable. These are the unknown to be determined subject by the constraints, which means it denotes or represents x1, x2 up to xn, and it consists of two variables. The one is dependent variable, another one is independent variable. Now let us know what is an objective function. A function which is expressed in terms of decision variable. It is the objective which is helpful for maximizing the profit and minimizing the cost. Zmax indicates C1 x1 plus C2 x2 plus C3 x3 up to Cn xn. But whereas the Z minimization, which means Z minimum cost, it represents C1 plus x1 plus C2 plus x2 up to Cn xn. Now, if there is a word given, profit, loss, selling price, cost price, or revenue, then it is called as an objective statement. Now, let us see what are our constraints. They always represent limitations in using of resource like laborers, raw material constraints, time constraint, labor constraint, etc. It is helpful for giving a inequality equation which is greater than or less than. Now let us know what is a non-negativity. It gives the decision variable which is always a positive value, x1 greater than 0, x2 greater than 0. Let us understand what is the procedure to solve a linear programming. The first step is to write down the decision variable of the problem in the format of x1, x2 up to xn. It depends upon the problem how we determine the x1 and x2. The next one is formulate the objective function which is to be optimized dependent upon the decision variable. It is depending upon the decision variable that whether the problem is Z max or Z minimum, which means it is for maximizing the profit or minimizing the cost. It will be determined by seeing the decision variables. The third step is to formulate the other conditions of the problem, which are right source of limitations in market constraints, which means in linear inequality equation, the term of decision variables are visible. The fourth step is to add the non-negativity constraint so that the negative value of decision variable do not have any valid physical interpretation. Whatever the formula we get, it always represents a non-negativity in a positive value. Now, let us understand this whole procedure with solving a simple problem. The problem says a company engaged in producing two models, namely X1, X2, which is performing three operations, that is painting, assembling, testing, and the relevant data are given below. These are the relevant data to our problem, which is sales price, hours of assembly, required painting for each unit testing. The one is model X1, model X2. The sales price is 50 and 80. Hours of assembly 1.0, 1.5, required time 0.2, 0.2. for each unit testing 0.0, 0.1. Now, this problem has three conditions. The first one is total number of hours available for a weekly is assembly hours 600 hours, painting hours 100 hours, and testing hours 30 hours. The next one is company wishes to determine the weekly product mix so that to maximize the revenue. The word maximize has been recognized here, which means it is a Z-max problem. We have to maximize the profit. The next one is formulate linear programming problem, which is LPP. So if we see this problem clearly, we can understand that we are having two models. One is x1 and x2, which will be our decision variable. We are having the sales price, that is our objective function, as it says maximize. So it will be 50x1 and 80x2. Then we are having the three time constraints, which is assembly hours, required printing and testing. So it is 1.0 x1 for x1, as we see 1.0 for x1 plus 1.5 for x2, and the less than or greater to is 600 because it is a maximization problem. So less than 600. Then it is 0.2 x1 for painting plus 0.2 x2, and the painting hours are 100 hours, which is less than or greater, less than or equal to 100. The last one is 0.0 x1 plus 0.1 x2 and less than or equal to 30 hours. So this will be our time constraint. So let us know how do we solve it. First one is decision variable. So as I said before, the profit will be x1. So the first decision variable is x1 model x1, x2 decision variable for model x2. The model x1 and model x2 is our x1 and x2, which is our decision variable. The next one is objective function. As we saw in the sales price, it is a Z maximization problem of profit. So we will take the sales price as objective function, that is 50x1 plus 80x2. The third one is constraints. We had three constraints. The first one is assembly hours. In assembly hours, assembly time constraint 1.0, which we saw in the table, x1 plus 1.5 x2 less than or greater to 600, which was given in the condition. The next one is painting time constraint. It has similar of 0.2, 0.2, so x1 plus 0.2 x2 less than or equal to 100. This 100 was given in the first condition itself. And the third one is testing time constraint 0.0 x1 plus 0.1 x2 less than or equal to 30. This 30 was also given in the first condition, and this has been represented in the table chart. Now the last one is to formulate a non-negativity. And as I said, a non-negativity is always positive. So x1, x2 greater than or equal to 0. So by this, we complete our problem, and thank you so much for your valuable time.